first of all, yeah, thank you so much for the introduction. I really appreciate it. Super excited that Xander went before me. I think I'm going to talk a little bit about streaming in my talk, and they can integrate with a bunch of different platforms. DAGWorks could totally be one of them. Yeah, so hey folks, name is Elijah. Jim introduced me, but I'm going to be talking about something I'm really excited about, which is the open source library Hamilton, and how you can use it to build out feature engineering capabilities. Specifically, how you can use it to write your features once and run them everywhere in different contexts. So today, what do I want you to come home with? I want to convince you that 1, writing portable feature engineering code is hard. 2, state-of-the-art approaches aren't flexible and powerful enough. I put a little spicy emoji by this because you're hearing about a lot of interesting state-of-the-art approaches, and I think they're all amazing. I want to offer sort of a slight alternative or a very different way of thinking about it. Hamilton can help you write code to run in multiple contexts and keep your code organized and clean. And Hamilton is easy to get started with and easy to use. So first, a little bit about DAGWorks. We're aiming to build the unifying layer for data, ML, and LLM pipelines. It's all open core, so we have a paid product, but that's not what I'm talking about today. I'm not selling anything. I'm going to be talking about Hamilton. Everything here is free to download and use and all open source. So you can install it on PyPy, on Conda as well, easy to get started. You've got documentation, I'll give the links later, and you can try it out at tryhamilton.dev. This is a website that uses Pyodide to have a sort of interactive Python experience in your browser. You can explore Hamilton, run through a few examples and sort of learn the basic concepts. So on the agenda today, first, I want to talk about the problem or the challenges with feature engineering. Then I want to talk about the solution we came up with, Hamilton. Next, I want to talk about how you can use Hamilton to write your features once and run them everywhere. I'm going to apply this towards batch and streaming mode. And then I'm going to talk a little about additional benefits of Hamilton, what having a Hamiltonian code base does and how it sort of can help you. And finally, talk about some open source progress and community updates. So what are the challenges with feature engineering? Well, I want to look at a common scenario that's based off of something that I saw at a previous role in e-commerce, but I think is generally fairly widely applicable. So customers will fill out survey results when they're signing up, when they have something they want to tell you. Your model makes predictions, and the goal is to get the survey results, featureize them, and send them to the model so you can make accurate predictions. What are the caveats here? Well, you've got streaming survey results trickling in. As you just learned, the infrastructure for that can be fairly nuanced and complicated. Data comes in dumps nightly, so there's batch data to handle. Multiple teams are working together to do this if you're at a bigger company. So you've got your feature teams, your infrastructure teams, and your data teams. And features are derived from other features that are derived from data, right? So it's functions of functions of functions of your raw data. So visually, this looks something like this. You've got your customer surveys coming in, you've got your batch data coming in, and you've got your live browsing data coming in. You put them through these feature transformations, which I'm going to break into map, aggregation, and joins and queries as sort of the standard shape. And then you want to do model training or inference, right? We're going to be focusing mostly on feature transformations with a little touch of inference during this talk. So the context you'll want to run this in to actually make it clear, you could want to run in batch on tables in your data warehouse for training data, run inside a streaming processor such as DAGWorks, or DAGWorks to organize it all, or Kafka as a processor for near real time, and transform browsing data live. We're not going to focus on that one, but it's sort of natural to extend this to true online versus streaming contexts. And complications. You want to ensure that the data is the same in all contexts so that you don't get a difference between your training and your production serving context. So how do you handle joins or alternative data sources in non-batch mode? And how do you include aggregations in streaming mode? These are all sort of fairly complicated things. And how do you track lineage, versions, et cetera, for different data sources, right? These are the things you have to think about when you're having a feature pipeline that's run in multiple different contexts. So back to that spicy point I made at the beginning, I want to argue that the current approaches kind of fall into two different sides of a spectrum, right? So on the one side, there's context-specific execution. And what this looks like is you write batch code and you write streaming code. These are two separate pieces. And they, so two separate ways of doing it. And you, the first one, you have as much power to do each one in whatever way you want, but it can be cumbersome to manage, right? You have two separate ways of writing code. You have two sets of versions, and the big question is, do they match, right? On the other side of the spectrum, you've got a single feature DSL to unify. So you got to learn a new way of doing things. It can sort of be opinionated about how you do these aggregations and how you do these joins and make it very powerful. And I think these are sort of really interesting and fascinating, but it can be tougher to grok, limited to specific operations, and highly opinionated on how you do aggregations and joins, which often I find are as much an infrastructure question as they are a modeling question. So I want to propose something kind of right in the middle. And the idea is, can we write normal Python code that is dry, meaning you don't repeat yourself, applicable in all settings, so you can reuse pretty much all the same code, fully customizable. You decide how to do joins differently, you decide how your aggregation approach, you write map functions however you want, and you bring all your own infrastructure, and that are self-documenting and imply structure, meaning it's really easy to figure out exactly how what is happening in your feature code just by looking at the code. So I'm going to talk about how Hamilton is the solution we came up with here to solve this problem. And it comes from a very simple concept. So the idea is, what if every feature corresponded to exactly one Python function? And what if the way that function was written told you everything you needed to know about how that function worked? So in Hamilton, the artifact, feature in this case, is determined by the name of the function, and the dependencies are determined by its parameters. So if you've ever seen PyTest, it's kind of taking that idea of fixtures and adding type safety and sort of taking it to the extreme. And what does this look like? Well, just to be clear, Hamilton supports all Python objects and any sort of data frame library. It started with Pandas, so I'm going to kind of use that because it's something everybody knows. But really replace it with Polars, PySpark, et cetera. There are different sort of nuances, but it'll all kind of work the same. And you can have Python objects, whatever you want to pass between. It's just Python functions. So instead of writing operations on a data frame like you would here, DFC equals DFA plus DFB, DFD equals transform of DFC, you declare your features as functions and write them out individually. So as I said, the output corresponds to the function name. So this is creating two features, one called C and one called D. And D depends on C, and C depends on A and B, which aren't defined here. So they could be something from the outside world, or they could be another upstream feature. So to tie this all together, what do you actually need to run it? Well, this is a full hello world. You've got your functions, each of which defines a feature. And then you've got a driver to say what and when to execute, right? So all the driver does is import your modules, load it up, and then execute, pass in some input data. You can think about the driver, the functions is setting up delayed execution. The driver is interpreting that and actually running it. So to sum it all up, for each transform, you write a function. Functions declare a DAG, which is a directed acyclic graph. If you're not familiar, it's just a way of saying, like, run this, use this data to run that, use this data to run that, etc. It looks like a flowchart. And Hamilton handles this DAG execution using your driver. And it's as simple as that. So you're probably asking, doesn't Hamilton make your code more verbose? You have to write now functions instead of individual lines sort of operating on the same data frame. I want to say yes, but that's not always a bad thing. And in most cases, that's probably a good thing if you do it right. But when it is a bad thing, we have decorators. So these decorators you can think about as sort of macro DAG operations that enable you to sort of change the shape of your DAG and make it a little more concise. There's a bunch of them, and there's sort of a whole algebra here. But the one you need to know about for this talk is called config.when, which allows you to use a static configuration parameter to choose between different implementations of the same sort of node or function. So now let's talk about how you can use it to write once and run everywhere. And the basic premise here is that we're going to have one, and this is where I a little bit led you on. It's not just one creature per function. For most functions, you're going to have just one, and you can share the vast majority of the code. But using that config.when, we're going to allow you to swap out implementations to choose exactly how to work, right? So I should have probably had an asterisk by write once, run everywhere, but I kind of like, I think this really is like a good way to do it because it allows just the flexibility and power for the more complicated operations, and everything else, you can run the same stuff. So with map operations, we're going to treat single versus bulk operations to be equivalent. Oftentimes, even the single online operations, you're going to want to be running in small batches. So, and you run vectorized. Aggregations, you're going to choose, do you store your aggregation, compute it on the fly, update regularly, etc. For joins, you can use we're going to use a query instead of a join, although there are other ways to do it depending on the data size. And again, for aggregations implements, you're going to implement just the small pieces that differ between them. So back to our scenario, remember e-commerce survey data coming in. we've got a set of simple map operations. Say you have a raw survey data where the customer inputs their budget, gender, and age, just sort of spitballing here. Derived features are, is their budget high? Are they a high roller? Is male, is female? Joins, you've got the time since the last login, which is a function of sort of the client ID and the login data. And aggregations, we're going to normalize the age. These features are kind of just made up, but the shape of this isn't too far from something that I've seen in real life and that you've probably encountered. All right, so what does this look like in batch? We're going to go over a full sort of working example of code and show how the DAG changes along the way. But first, this setting here. So the goal is to compute features and infer the model in batch, right? So we're going to do feature calculation and then model inference. Kind of if you were doing like a snapshot thing, it's pretty trivial to think about how you replace it with the actual training piece. And the context, we've got a database with raw survey results, another database with client login data, so we can get that information. Say the model is already trained. Again, I said you can use this for training, but we have a model object that we can access. And the data is of a reasonable size. That's just because I'm going to be using pandas, but Hamilton can work with any data frame library and has sort of tools to help you scale up pandas even. So what does data loading look like? Well, we actually do have some specific data loading adapters and decorators, but for now, we're going to do some very simple code, create a connection, load from SQL, and then we're going to have 4 columns here, 3 of which are features we cared about, budget, age, and gender. And the last is client ID, which forms the spine, right? So this is just a single node to start loading your data. And this produces a DAG that looks like this, right? We've got our survey results database and table. Those are strings coming in from the user. Then we get survey results and we split it out into separate columns. So now let's do the map functions, which are derived features on top of our features that we just extracted raw. Let's say we want to get is male, is female, is high roller. These are sort of very simple implementations. You can imagine these getting more complicated. One of the nice things about Hamilton is it's separated. Each one of these is separated into a specific place. So if you want to change it, if you want to sort of understand exactly what's happening, that's fairly easy to do. Now that we've added these, you can see we've got 3 more nodes, is male, is female, and is high roller. And we're starting to build out our DAG. And the point I want to make is one of the cool things about Hamilton is you can sort of take these DAGs and add extra pieces to it and start building it iteratively and composing it to turn from a simple data loader into a more complex data pipeline. Now, what are our joins going to look like? Well, we're going to do a join in memory, but you can easily do a join in your warehouse if you want. So this is loading your client login data, getting the last logged in, which is a merge there, and then a time since last login. Pretty simple, which is just a subtraction. It's a map operation. And you can see we've added another section to our DAG, getting another feature that we're going to want to use in our model. Aggregations. We're going to do the same thing that I talked about earlier, where you're not using necessarily pandas series, but you're using Python objects, taking a series and turning it into a float. So you get mean, standard deviation, and then normalize it, which is just a map operation. And finally, we've got that added to our DAG, and we have got all our features. So we've got aggregations, join, and map operations. And finally, we want to do inference. In this case, I've just defined model data to make it very explicit what the model is taking in. There are other ways to sort of join these series that you can use in Hamilton. This is just a way to make it very clear. And predictions, which take in a model that you pass in from the outside world, as well as the model data, and run your prediction. So you've got predictions on top of your inference, and this is the entire batch DAG. To put it all together, here's what the driver looks like. This would be in your etl.py script. Say you're running an Airflow or wherever. You would import your features, run it, and pass in just the inputs you want based off of sort of your setting. Simple enough, easy to run. All right, so what does this look like in the streaming mode, and what specifically do we have to change? Well, let's set up a context first so we know what we need to build. You see you have a service to give you client login data. You've stored aggregations from training. So we have those means and standard deviation. And your goal is to be near real time, so to predict as soon as raw data is available. What are the changes that are required? Well, we have no aggregations available, right? So we have the stored aggregations training. We'll use that. We want to swap out an external join with an API call. So say we have a service, as I said, to give us the client login data. We're going to be using single datums, not data frames. We kind of treat them the same here. I found that in most cases, the performance hit of using single items versus vectorized stuff is almost negligible. But there are ways to sort of vectorize in Hamilton too, if you want. So we're going to be using this decorator config.when to swap out the features you need to change. There are 4 different things here. So note we've got 4 things that are different versus like 20 or 30 features that we've defined overall. And this is loading in the survey results, loading in the last log data, and loading your scalars here. Note that we have this sort of double underscore thing after the feature name. All this means is Hamilton's going to chop it off, and it's kind of a clever way of defining two features that point to the same thing in the same file, right? And we're doing config.when mode equals streaming to say, oh, in streaming mode, we're going to do it this way versus in batch mode, we're going to do it another way. And what does this look like? Well, the DAG is actually simpler because we're loading data from external sources, so there's more complexity pushed outside. But comparing it to the other one, we've got the joins, the maps, and the aggregations. Or we got the data loaders I've highlighted, the joins and the aggregations that are different between them. The maps are all the same, as are most of the sort of pieces within those in the glue. So what does the driver look like? This is kind of like generic streaming stuff, taking a list of records, output a list of predictions, probably a list of records. In this case, I just made a list of floats. Set up your configuration, instantiate your driver, and process your records, which all it does is set your inputs from the records and execute it, right? So we've got a feature pipeline that works in batch or streaming, and most of it is exactly the same. And you know everything that's different. So it should be pretty clear to figure out what's going on and figure out what the corresponding batch operation and streaming operation is. All right. So Hamilton gives you portable feature engineering code, but also gives you a host of other benefits. So because it lets you write these Python transformations as simple, or these transformations as simple Python functions, they provide everything you need to know. So unit testing is really easy. They're all just plain old Python functions. You can unit test individual pieces or unit test an entire path. For documentation, all you need to do is use the Python docstring. For modularity, you naturally have it broken into small pieces, and the small pieces are organized into modules, so it makes modularity really easy. Your code naturally forms a central feature definition store. So it's not a data catalog per se, but it's a very valuable thing to know exactly where your data is coming from, and you can sort of visualize the DAG as well. Debugging, you can execute functions individually and set breakpoints, even pass in mock data fairly easily. And for trustworthy data, to make sure your data is trustworthy, we have validation included out of the box. So we have all sorts of cool validators, including a Pandera integration that's built into Hamilton. Right. So how does this integrate with feature stores? Because we're at the Feature Store Summit. Hamilton is kind of the transform layer. It actually works in basically anything that runs Python. So HopsWorks, Feast, Tecton can be the storage and sort of moving around stuff layer. And we actually have a blog post of Feast integration here that I'm really excited about that shows a few different ways to use Hamilton to make it easier to manage Feast features and manage Feast constructs. All right. So taking a step back, it's not just applicable towards feature engineering, although that was sort of the bread and butter and how it started, but it can improve code wherever Python and data are involved. So for LLM pipelines, we've got users online writing retrieval augmented generation and fine tuning. For ML training pipelines, a lot of people writing sort of training pipelines. You can see that's not actually that different from what we showed you earlier. And for sort of general data engineering pipelines, we've got all sorts of integrations with pandas, PySparks, Polars, et cetera. And it's pretty complementary with most existing infrastructure. It's really a way of organizing your code and doesn't really care about how you run it. So if you've got Airflow, dbt, Prefect, Dagster, et cetera, it's sort of complementary with that. It kind of is a different way of doing chains in the LangChain, although you can use them together nicely if you want. PySpark, it's complementary. We have a whole blog post and a whole integration about using PySpark. With Kedro, it's sort of complementary to the structure, if you like the way that Kedro is organized, and replaces the sort of way that Kedro builds DAGs. For Ray and Dask, it's very complementary, and the goal is for it to up-level your sort of software engineering skills, so that you're thinking less about infrastructure and logic at the same time and can sort of separate them out. Okay. Finally, a note on open source progress and updates. We've got a thriving community. This is we have 110,000 plus downloads. These are a bunch of users that we know from just having chatted with them. There's a whole host more that we don't know, and others that we sort of talked to, but they're all using it for sort of critical models in production. We have a growing set of core contributors, a full company dedicated to building it. That's us. We're looking for contributors. So we have a whole Hacktoberfest thing going on. We've gotten a bunch of engineers who've wanted to really sort of like start contributing to open source, and a bunch of tickets that are easy to get started with. We're looking for bug hunters and user feedback. Nothing better than the more people telling us problems and things they like about our code, the better we can make it. All right, in progress, we're working on more expressive APIs, so flexible loading and materialization. I didn't show it here, but we have all sorts of ways to decouple the loading of the code from the actual transformations and saving of your data. New higher power decorators is really exciting, ways to sort of perform macros and make it extremely expressive. And we're always listening to new ideas. For the execution side, we're thinking of building out the ability to compile a Hamilton code to, say, Airflow. So you write your code in Hamilton, which is easy to think about, press a button and it gets compiled down to the right Airflow DAG. Snowpark integration, and a whole host of ideas. We've had a bunch of good user interaction here from open source. So give Hamilton a try. We'd love your feedback. Try hamilton.dev, easiest way to get started. You can install it on PyPy. Please give us a star on GitHub. If you like it, we really love knowing that people are sort of like what we're working on. You can create and vote on issues on GitHub, join us on Slack, and for those later, there's a link to a blog post that goes through this talk and code to play with. So you can download all of this and get started and sort of adapt it to your case. All right, so thank you so much. I really appreciate your time. Really excited to be here among everybody. Really interesting talks. Here's links if you want to like yell at me online. QR code to the GitHub repo. Thank you so much.
That's brilliant. Thank you, Elijah. And it's great to see an in-depth discussion of some of the capabilities of Hamilton.